Is everybody appreciating the chicken nut guts? Is that, I hope everybody likes that. Where am I?
Yeah, it sparks joy for me.
Me too, weirdly. And it's hard to know which brings me more joy, the nut guts or the spinach. Okay, there is the lecture right now. And I'm doing this thing I always do, which is, let me drop it over into the schedule. And if I do that in real time, it always happens. So that's going to be the November 10th lecture. All right. Okay. Welcome, everybody. For the regular crowd who's going to like stumble into this thing on Tuesday, sorry, wish you were here, but you are here now. Okay, so here's what we're doing. We're on chapter 6, and what we're actually talking about is stepwise refinement and a little bit about debugging. And we might finish this like tonight. And that would be fine if we did that. We good? Yeah. We're all good on that. Okay. All right. We were talking last time about this idea, right? I think I was beating the tar out of the concept that you don't know where to start, but that's not true. You do know where to start. You just don't know how to finish. And it's a stepwise process. You do a thing, you make it better. Then you run that with that for a while. Then as you run it, you learn a little more. And then as you learn a little more, you figure out another way to make it better. Have you ever, I'm going to give you an example. And I should have already had this ready, but I didn't. I want to just show you an example. Let me see. What's a good example? Here's a good one. Let's do this. Hold on. I'll have this in just a second. This will not take me long. What are we on? We're on chapter 6. Okay. I'm just going to pull up an image, and I just want you to contemplate this for a second. And I think it, no, shoot, is that the one? What is that? Come on. Sorry, I thought I had it and then I didn't. There we go. This will work. Okay, hold tight. It's going to be so worth it. This delay right now, so worth it. You're like, I don't think so. And I'm like, no, I think so. Here's why. Check it out. I just want you to look at this picture. Have you ever just been like, whatever, you're just driving down the road and, few of you have probably worked at factories like this, right? I don't even know what this factory is. It doesn't matter. But here's my question. How do you create a factory like this? How do you see the level of complexity? You know what I mean? There's the stairs and the thing and it weaves and it's three-dimensional and, there's this thing, there's steam comes out of the one thing and, right? It all looks so crazy. And you look at this thing and you kind of go, it kind of blows your head, right? Just a little bit. I'm not the only one, right? I mean, that it kind of throws you a little bit because you're like, I don't know how in the world you do something like this. But I will tell you how in the world you do something like this, because code is potentially more complex than this. You'll be involved in software projects that are way more complex than this, okay? So how do you do it? And the answer is you don't just sit down on day one and start drawing this factory. You don't. You start with sort of some core ideas like, again, I don't even know what this thing is.
Frozen for anybody else?
What's that? Am I frozen?
Yeah, me too. I was just.
Do I need to? My video's frozen? Is my audio frozen? Okay. Hang on.
Oh, it's back.
Wait, I'm back?
Yeah,
Audio and video?
it's a little delayed, but yeah.
Okay. Because I can. What do I sometimes have to do? Just like kill my OBS and relaunch it? Or kill Discord and relaunch it? Does that seem okay now?
Yeah, it seems okay.
Yeah, it looks fine.
Okay. Because I can kill. Sometimes I got to kill Discord. Okay. So what I was starting to say that probably got lost is you don't start on day one and just draw this picture any more than you write a million lines of code, and it's all like in your head, and then you just start writing the million lines. You don't do it like that. You start with a kind of a core idea, like we're refining petroleum, or we're processing recycled something. You know what I mean? Recycled restaurant grease. I don't know what this is doing. But the point is that you start with sort of some core ideas, some core principles. Like, well, we need a little vat that we can put the grease in. And then we prototype it. We're like, okay, yeah, we can get the thing. But like, this thing has to get really hot. Okay, we've got to figure out a way to heat this thing. So we add the ability to heat it. Then we're like, that gets really hot. Now we need to insulate it. Okay, well, it turns out that when it's too close to the ground, it has some
Dr.
properties.
K, we can't hear you.
Ugh. Okay, I'm gonna relaunch my Discord. Hold tight. Where am I? All right, so I got audio now, right? Am I okay on audio?
Yeah, I can hear you.
All right, extra monitor streaming. Yeah, okay. All right, let me get my video back up. And I was telling such a great story, by the way. Right back.
I think it was a problem on one student's side because the rest of us could hear you, it seems like.
Oh, okay. Okay. So is that better for everybody right now? We okay? Audio, video?
Looks good.
All right.
Yep.
So here's the thing, right? So imagine again, I'm talking about something about which I know nothing, which is, refining some whatever, okay? Let's just say we're recycling restaurant grease or something, right? So what I was starting to say is you figure out like, okay, to do the thing, we know what the basic recipe is. You do this thing, you apply this chemical, there's some heat, right? The steam goes off there and it's just chemistry. And then, some substance flows down this tube. And then you discover that if the tube isn't above a certain temperature, then it'll clog it up. Okay, now we have to figure out a way to heat the tube. So you start heating the tube. Then you're like, okay, that works. But it turns out it overheats and causes a problem with some other thing. Now I got to create a separation between those things. And this thing has to be, it turns out, it gets too hot once you reach this temperature, and I got to insulate it. And it turns out it causes all these problems with the instrument readings on the ground. So I got to put it up in the air. And then it turns out that I've got to, it releases steam, but if it's too close to the ground, the steam interferes with something else. So I got to make it even taller, right? And now that means I've got to run pipes. And it turns out when your pipe gets beyond a certain length, it has a certain problem that didn't happen. Do you see where I'm going, right? It is a sequence of stepwise refinements to get to a factory like this, which again, I don't even know what it is. I just know it's just really complex. And I look at it and I kind of go, okay, wow, crazy, right? But you realize that every single pipe, the bend on that pipe, there's a reason for that. It's a compromise of some form. Every railing, every, whatever. And it starts with a basic idea. And same with look at steam engines or old railroad, just railroad trains, engines, right? And how much stuff. It didn't start off like that. Look inside the hood of a modern car compared to, an old 59 Chevy pickup, right? These things get more complex as you solve more problems, and it gets kind of better and better and better. Code does the same thing, okay, when you build software, all right? So you don't need to be intimidated. When you look at this, you don't need to be freaked out if someone says, yeah, you got to build this. You're like, okay. You could just go, I don't even know where to start. Or you could just say, well, what does it do? What is it? And it's like, well, it's a petroleum refinery. Okay, what does that even mean? Okay, well, here's what it means. You start asking questions. You start exploring. And you break the thing down to its basics, and then you grow it and build it and expand it. Eventually, there's wires and tubes and stuff going everywhere. Okay? And it looks crazy complex. Okay? But really, it's a manifestation of a bunch of learning that's happened. Little by little by little by little. Okay? Does that kind of make sense? Like why you don't need to be intimidated because you're going to build 1 million lines of code. Just start by building the basic structure of what you know needs to happen. And then you'll find as you get in, you'll learn more. And each part will get a little better. And you'll discover new problems. The new problems will require, other solutions, and it'll get more and more complex as you go. Okay? But you don't need to worry about it or freak out about it just because you don't know going in what everything is. All right? That's the idea of stepwise refinement. All right? And I think we actually talked about this already, looking at potential solutions, breaking it down into solvable chunks. And there's also that part where you sort of evolve as you go. And then you kind of put the solved chunks back together. Okay, so here is an example of ways to do certain kinds of tasks, okay? And these are going to relate, no shock, this is going to relate to assembly language, okay? But it's also going to relate to just programming, to software. One is there's some task that has to be decomposed, right? We have to do this decomposition of this task. We can do the thing sequentially. We can do it with a condition, or we can do it iteratively. And it turns out that different kinds of tasks, involve one or more, right, or all of these different ways. All right. So what we're going to do is we're going to break this down to kind of give you a sense of it. To try to help you think about programming in a little bit more of a complex way. You've been all the way down at the instruction level, right? Here's an instruction. How do I write programs like that? How do I solve bigger problems like that? So here's an example, okay, again, of the sequential, which I think, we're gonna break each of these down. The sequential, the conditional, and this iterative. I think that was the order, yeah. Okay? So here's kind of what, sequential is easy. That's the straightforward part. I got to do this first part, and I got to do the second part. That's it. And it's just a set of instructions. There's no conditional, there's no branching, there's no jumping, none of that. No control codes, none of that stuff. I basically just start at this instruction. I do all the instructions I need to do until I'm done. and then I do all the instructions I need to do till I got the second one done. That's it. That's sequential, right? And a lot of the Betty Crocker cookbook stuff is going to fall into this category. You know, do the thing, make a pan, get the thing ready, then do the next thing, right? And there's a bunch of sub-tasks. Mix the dry ingredients, then mix the eggs and the other ingredients, and then, you know, preheat the oven, right? There's just a bunch of sequential tasks, and you just, you know, work your way through. You can even think of, like, if it's like add 2 eggs, it'll say like add 2 eggs. Well, you could think of that just conditionally. You could think of that iteratively, but you can also think of it as sequentially. Add the first egg, add the second egg. Done, right? I could also be for all eggs, and I could think of it more like a for loop. But sequentially, it just do the first part, do the next part. That's it. Right? So that means what happens in the code is that the program counter starts here, goes, and then when it's done, you know, and then it keeps going. Ta-da! Nothing crazy. Let's do conditional. And this is the flow chart, okay? Right here. And here is what this would look like in the LC3. So the first thing we're going to do, and by the way, we're going to do this in the case where it's true. The first thing that's going to happen is I'm going to come in and basically generate the condition, get the thing set up for the condition. And that's what this is doing. The program counter just goes through and sets up things to be ready for the condition. Here is where I'm testing the condition. In this case, anybody recognize this opcode? 0000. Anybody? That's
Branch.
Yeah, it's the branch instruction, right? And it's going to be based upon some condition codes, right? Which ones do you want me to look at? And where am I going to go to? And if it's true, I'm going to jump over to here. The true case maybe jumps me here, right? Because if it's true, I take the jump. And now I do subtask 1, which is, you see it over here. Let's do it again where it's false. You do the setup. I get to that same test, only it's false. I don't take the jump. I drop straight through. But when I get to the bottom of that subtask, what do I have to do? That's another branch instruction, right? What are these 3? Anybody remember? These 3 bits?
It's like a guaranteed jump.
Yeah, exactly. Those are the NZP. I'm saying those are the NZP bits I want to consider. Let's consider all 3. If any of them are on, well, that's by definition, 1 is always going to be on. So I will absolutely take that jump. Sorry, I kind of jumped to the next slide, but right, I'm going to take this jump. So that is how I've, and this is a little bit clunky when you start to think about assembly language this way, And again, this is just a conditional jump, right? I come, I check, and I'm either going to drop in here and bounce around, or I'm going to bounce around and then just drop through. Okay? One more time real quick. When it's true, I take the jump and I skip around subtask 2 all the way to subtask 1, and then I just fall through. When it's false, I don't take the jump, I just drop straight through. But if I didn't have this branch right here, I would do subtask 2, and then I would drop through and I would do subtask 1. I got to jump around subtask 1. Boom. Okay? That's conditional. Okay, here's iterative. In the case of iterative, you remember, I'm going to just say for everything, for all the numbers in range, for all the whatever, right? Boom, boom, boom. I'm going to do this thing over and over and over again. I'm going to check my condition. If it's true, I'm going to do the subtask while the condition holds. And when that condition no longer holds, I'm going to jump out. Okay? So I set it up. I set up the stuff. And then I'm like right here. And what I'm really asking myself, this, by the way, this true and that false are different from the true false of this instruction. What I'm doing here is I'm saying if we should keep going, then I'm going to drop through. But the condition in this instruction would be false. Okay? The branching condition says, yes, my condition holds, because that's how for loops work, right? While this condition holds, keep looping. Manifests itself over here with a false condition. If this thing fails, I'm going to drop in and do the subtask. Then I have to hard jump back up to the top where I recalibrate my condition. Redo whatever that thing is, like increment I, grab the next one, whatever it is. Check again. And then when it no longer holds, we're going to kick out. Okay? So this one here, again, this is the true condition when I take the jump for the instruction, but it's false relative to the question I'm asking. And that's another skill to kind of acquire when it comes to assembly language programming, is the little bit of it's an abstraction separation. The question I'm asking is, should I continue, yes or no? If I continue, that condition has to be false. If I'm done, the condition has to be true. You've got to get that in your head. Here's a little interlude on a flowchart. I could, do I dare? Do I dare?
Be bold.
I don't know if I should be bold. It might be really dumb.
I can do it if you want.
No, I'm going to do it.
All right, make it happen.
I feel weirdly courageous and like I'm about to be blocked. Like I'm about to receive a video takedown notice. I'd like to thank the Beatles for this moment, without whom this flowchart would not have been necessary. No sense pushing my luck. Okay, so anyway. Yeah, this is, I don't know. I find this really, really funny, especially this part here. If you remember the classic song, right? The na, 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 na. Although it's not quite right. Well, it does go na, 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 and then it jumps back up, hey Jude. But it's not exactly right. I need to make a better one. I need to take a sad flowchart and make it better. Okay, so here's what we're going to do. We're going to take one that we already talked about before, and I'm going to break it down. We're going to break it down and start to make a little more sense. I feel like I just did this. Did I do this last time? I don't think so. I'm probably having a flashback from spring semester. Here's the idea. This is my spec. We did one like this where we were doing the code. I remember now. We had code, remember? We had like 10 or 12 lines of code in assembly. So we're going to input a character, we're going to scan a file, and we're going to count occurrences of that character. We're just going to look at one byte at a time in that file. And then we're going to display on the monitor the number of occurrences of that character. We said up to 9, which I don't think our code actually did. Okay, that's the spec. So you could say, well, that's it. That's what we're going to do. Well, that's not quite good enough, right? I mean, by itself. You got to break this thing down a little bit, right? So what jumps out immediately? What are some discrete chunks you can look at and see as unique things that need to happen at a pretty high level? What say you? What say you, Buellers? Young Buellers, what... Well, there's only 3 sentences here. How about take some input, do the thing, and spit out the output? How about that, right? So you can break it down. And the point just being that I can when I can break the thing down, then it's like, ignore the other part. Let me just focus on this part. And it'll kind of blow up. Okay? So what I'm doing here is input a character. I'm blowing it up to kind of, first of all, it's sequential. It's just a set of steps. Initialize. Get my memory variables where they need to go. Input a character. Set up a pointer to the first location in the file. Get the first character. Get things ready. You know what I mean? Zero out the register that's going to hold the count. Do that kind of... And this is, by the way, a bit of a deep jump. Because you can still say, set it up, input the character, go. You know what I mean? You can still break this thing down. Scan the file. That's right here, which is actually a little bit complex. But that's also sequential. And then here's another part. Then you didn't display on the monitor. That's also just sequential, right? So it's like, do all the initialization, scan the file, and spill the results. Now, do you see how much bigger it's all of a sudden gotten? And you've also identified discrete parts. Also, each chunk gets, wants to be broken up. We'll kick it over here and let's go again. Let's look at this one. Here's some specifics. We got to have a counter, and we'll just decide that R2 is going to be our counter. And R0 is going to hold the input from the keyboard because that's how the LC3 works. R3 is going to be the address of the first character because we just decided. And then R1 is going to be the first character in the file. Again, we just decided that'll be where we'll put that stuff. So we're making it more specific. Now, and by the way, that's again sequential. But now when we say scan the file looking at every location, that starts to sound like iteration, right? And so here's now, I can think of this as the flow chart, right? Like, am I done? Yes. If I'm done, I kick all the way out. If I'm not done, test the character. If it's a match, increment the counter. Get the next character, right? Loop to the top. Am I done? Am I done? Am I done? Am I done? And I don't even remember. We did one. Remember where we were using a sentinel of -1. You know, that was one thing. We can also go till we get to the end of file. Is another way to stop with a sentinel. You know, you can also just go until you get 9, and that would be another way. That would be a little bit more, less of a sentinel, and more of just a counter. All right. So let's kick it over and blow that up a little more. This guy here, we just blow it up into these 4 specific, that's not really changing much. We're just being a little more specific. This one here, test the character. If it's a match, increment the counter. So we can kind of break that up into 2 spots, right? Test the character and increment if it's a match, or, get the next character. And then get the next character. So we're just blowing it up a little bit. And then to display the count on the monitor, we can blow up a little bit as prepare to display it, and then display it, display the output. But do you see how we're doing this? Do you see where it's going? You start off with this little 3 sentences, and now we've got this kind of this picture that's growing in complexity. But we don't have to know all of that when we start. We just look at each step and go, well, which one kind of wants to be, looked at in greater detail? Nudge it over. Now, this one here, we're going to kind of go, that's okay for now. Let's look at this part where we test the character, and if it's a match, we increment. That's conditional, right? Look to see if it's the right match. That's conditional. So we blow that up as a flow chart. We already have R1, which is that first character. We have R0 as the input value. Well, R1 is the character. It's always the character. We just check to see if they're the same. If they are, then we'll increment R2, which is the counter. Get the next character, kick back up. If they're not the same, we just skip the increment and we kick back up. And see, are we done? We'll get the next character and we kick up either way. All right. Getting the next character says that we increment R3 because that's the pointer in the file. And then we just grab what R3 points at and put that into R1. So R1 always has the next character. Okay? So the point just being, we're not even done. We're not even done. We haven't written the code. We haven't taken this all the way there yet. But notice that we just started with this, 3 sentences, and when we're even part of the way done, we're here over here on the right. You see how this starts to look? Do you see how this looks more like the factory? You know, can you kind of see that has more of a factory look? Pipes running everywhere. You know what I mean? It starts to get a little bigger. And yet over here, it's just like refine oil or refine, kitchen grease. And it turns into all the little steps that go into that, each of which has to be coded in assembly language or in our programming language if we're doing any kind of, design. Or in the case of the factory, has to be a pipe, a fitting. Every pipe has a fitting. There's nuts and bolts and all the rest of it. All that nuts and bolts and stuff. Okay? So, that's all I want to kind of go through relative to systematic decomposition. Okay? It's a systematic process. You don't need to freak out. You take the thing you're trying to do and you just try to understand, the natural things you have to do to get from point A to point B to do this task. Sometimes it's sequential, sometimes it's conditional, and sometimes it's iterative. And those are kind of the big, kind of really common ways of thinking about programming. Cool? Are we cool? Anybody ready to surrender? You with me? Stay with me. Don't surrender. What we're going to talk about now for a little while, and I think we will wrap this up. I might be cursing myself by saying these words that I think we're going to wrap up. But I want to talk about debugging. This is a critical skill for just being a programmer, being a software engineer, being a computer science major, a data scientist. Anything that you have to build software, you have to understand how to debug stuff, okay? So it's very similar to what I was saying about design, which starts with throwing up your hands is not a strategy, okay? That's kind of number one. And some of you might have children, but all of you were children. And maybe you had younger siblings, so you were old enough to be aghast at how bad small children are at finding their shoes, right? Why is that so hard? Somebody answer me this. Why is it so frickin' hard for a small child to find their shoes? And if you have anything you want to offer, it's fine. But I will tell you that the number one problem is that they lack debugging skills. Okay? They lack debugging skills. Debugging skills is simply about the idea that something's wrong and you figure it out. That's it. The engineering ethic is all about figuring stuff out. It's not about knowing the answers to everything. You don't study engineering, or computer science or any engineering related field. You don't study these things in order to know the answers so that when you encounter them, you will know the answer. No. You're acquiring the skills so that when you encounter the next unknown and unknowable situation in advance, when you encounter it, you're like, well, I don't know what's going on here. Let me figure this out. What do I know? Let's start with what I know. What can I know? What do I know that I don't know? Right? It's that process of debugging. And the primary task is learning. That's the critical thing. The primary task is learning. If you actually knew what was going on, you wouldn't have a bug. Right? If you knew what was going on, right? Now here's one of the things. When I'm trying to help somebody with their code and they say, Now, I know it's not over here. Okay? You know what I assume? Any Bueller? If somebody is, yeah, go.
You're like, recheck it.
Yeah, right. I'm like, if they tell me A, they have no clue how to get this thing to work, but they know that it's not over here, I usually figure that's probably where it is because it's the place they've been looking at the least because they were convinced that
Yeah,
wasn't
that happens to me all the time.
right. I mean, we do it ourselves, right? So I try to be aware of it in my own. If we like, what's the code I'm really confident about? But one of the keys is that as you build your software, you build it a little bit at a time and you test it. And you build a little more and you test it. You're debugging as you go. You know what it's supposed to do and it does it. You know what I mean? There's no guesswork. You're not like code a bunch of crap and then just pray. That is not a professional strategy. Okay? It might be fine for certain ventures. It's not okay for engineering, right? But if you can just build a little bit and know that it works, build another little bit. If you have to like make function calls, build your little function call structure and know that it works. Run it so that it's moving around. And I don't care if this is assembly or something higher level. You got to know that it works for what it's trying to do. Add the next little bit, a few lines of code, 5, 10, 50 in a high level language even, and then, test it. Know that it works. Should not be operating in guesswork, okay, or in the domains of faith. So other strategies, assume your own ignorance. You've got to assume. You got to be humble about the thing. Strategize about knowledge acquisition means, what is it I don't, you got to figure out what it is you don't know. You got to come to understand what you don't know and get rid of the blind spots, right? What don't you know right now? And that's a level of enlightenment. To know what you don't know in the moment is critical. And if you can't see that you don't know something, you're screwed, pretty much, until you can crack that nut. You know what I mean? You've got to get past to the point where you know what you don't know. Now you can go about knowledge acquisition. The primary task is learning. Okay. Back to the children. I had a bunch of kids. I mean, I still do, but they used to be little. I'm saying I had a bunch of little kids is what I really mean by that. And when my little kids were little kids, and they couldn't find anything, I would usually go into their bedroom, look for the largest movable object, a blanket, a jacket, right? And usually I would just like lift that out of the way. Because they would walk in and they would just look at the floor and they would be like, this is why it's easy to hide Easter eggs for 4-year-olds. I mean, it's easy to hide them, hard for them to find them. You can get really tricky. They don't have the debugging skills yet. They get a little older, they start to understand a little bit more about how the world works, and they build mental models faster. And but for these kids, I look at it, I'm like, and you're like, whew. And then you're like a magician. You're David Copperfield. You're just like suddenly the amazing Kreskin, and you're like, how did you do that? Oh, I don't know. I walked into your room and I moved the largest object. So this is key. This last part is key. It is better when you're stuck, when you get into the large project, for example, or even some of the smaller projects that you'll start to do on the way there. The homework will have you writing little chunks of code. And it might only be 10 instructions, okay? And then that'll also show up on the exams where you have to write these really tiny little sections of code. If you're stuck and you can't get it to work, there's a natural tendency to fake it till you make it. You're going to just do something and then see if that does it. And then you do something else and you see if that does it. And and eventually you just start chasing your tail. It is better to take the time to fully understand the code than to just start randomly changing crap. And by the time you've done an all-nighter working on trying to get something working, it is really, really better to go to sleep. than to think I don't have time. It is better to go to sleep, get a shower, and then grab something to eat, and then look at it fresh and take your code and whiteboard it. What is it exactly doing? Play computer. Okay, R1 has whatever. Now you have the advantage of the LC3 for this class. It's all right there. You can see the registers. Step and know what is supposed to happen. And what'll happen is you'll go like step, step, and then you're like, that should be a 1 and it's not. And then you're like, okay, I know that's supposed to be a 1 and it's not. Clearly there's something I don't understand, right? There has to have been something I did not understand for that to have happened, right? And a lot of times you're like, oh, the jump instruction needs a register or whatever. Or I thought I did the LEA and I thought it was an address. Then you just look in the register and you're like, that's not the address. You can see it, okay? You have to operate in the domain of knowledge and not in belief or faith or wish or hope or anything else, okay? Sometimes it's really time consuming, okay? But again, just understand that you're always limited by your knowledge, and the job is knowledge acquisition. That is the task for debugging, okay? If at any point where you don't know exactly what is going on, if you're guessing, then the time required to finish from where you are there's no upper bound. Okay? There is no upper bound on the time it'll take you to finish it until you close the gap and understand exactly what's going on. Okay? It's not enough that it seemed to work. Even worse, if the code breaks, it's not working, and then all of a sudden it starts to work, but you didn't do anything, be very afraid. Okay? Be very, very afraid. Self-healing code is also self-breaking code. Okay? You understand this is the voice of experience? You understand? Okay, here on. Let me show you the scars I've got. No, you understand that this is the voice of many, many scars going all the way back to when I was your age. I know these things because I have all the scars to prove it. The unspeakably stupid bug, that takes 20 hours to find, and when you're done, it's like, I just didn't understand how that instruction worked, but I thought I did, and I kept reading it a certain way. Yeah. Okay. Few more things. This is really, really key. You have to know where your program is correct and then exactly when it stops being correct. Okay? So if it's like, okay, at this point, you look at the instruction. I'm putting the address of that variable into this register. And you look at the address and it's like 3105. That's the address of the thing. You do the instruction and you look in register 1 and it's not 3105. You know at that moment that you suddenly went from it was working right to it's not working correctly. And you know that it is that instruction. And this is really key. You have to also know this. It is not that the instruction is working wrong. Okay? Most of the time, the vast majority of the time, the instruction is working just fine. Your understanding of what you thought was supposed to happen there is wrong. And it's bloody open book, man. You got the documentation. Read the documentation, walk through the instruction, read it again, make sure you know what it's doing. And if you're not sure what it's doing, write little test code until you prove to yourself how it works. Okay? Now, there's a thing that I call the Big Bang approach to testing. I don't have a picture. The Big Bang approach to testing it's basically, it's like, imagine that you had a jet airliner, a large airplane, and you never tested any of the components. Didn't test anything. Then you bolted the whole thing together. You sent it off the runway. About 12 seconds later, it's like, boosh. And then you bring in the whatever those people are, the FAA, right? to go sift through the rubble to try to figure out what went wrong. That's what some of you do. You write your program down on paper. Then you sit down and you type your program. Can I? Hang on a second. Don't. Do you want me to punch this monkey? Do you? Because I will. This is how strongly I feel. I'm not going to punch the monkey because, you know what? He didn't do anything to deserve this, okay? But some of you did. But here's what you did. You wrote your program, and then you sat down and you typed it all in, and then you ran it. That is the big bang approach to testing. You are going to suffer, and you are deserving of your own suffering in this instance by not failing to heed the advice of the sage, Santa-like character before you, Dr. K, who's trying to beg you to do this thing, not the big bang way. What you do is the first little set of things, put them in drop them in, and then, assemble it and load it, and then step through it. Yep. Okay, I'm ready for the next thing. Add the next line. See that it works. Add the next line. See that it works. And then you'll find your misunderstandings as you go. It'll take you slower to get there, but you'll get there faster in the end. Okay? It's like the tortoise and the hare. You'll be the tortoise that wins the race. I mean, seriously. Long time ago, I was a software tester. And after I was a tester and I was so paranoid about everything, I wrote software differently after that. And so ever after, when I would write software, I would write it slowly, painfully, articulately, if that's a word, and correctly. And if it wasn't correct, I would learn about it at the moment at which I was introducing the problem. Then I would fix it, and then I would keep going. I didn't have, 12 lines of code with 5 major problems or 20 major problems, right? I had 12 lines of code with maybe one problem in the last line, and then I would fix it, and then I would expand, keep growing the code. But knowing as I went that it was going to be fine, that it was going to work. Okay, does that make sense? And I didn't have to punch the monkey. So we call that unit testing. It's a small chunk of code that's a little unit, and I test that unit. Okay? And I know that it works. All right, thank you, Chris, for the... I wasn't looking at the comments so much, but the for iron range eggs, yeah. You forgot to crack the eggs, though, Chris. In all fairness, you really should crack the eggs and then put the inner parts of the egg in that bowl. Okay. Debugging tools are helpful because they help you to acquire knowledge about the details of your program's execution, of what you've done, of your code, okay, that you wrote. How are we coming? Do I have one more? Yeah, this is it. More strategies. One, in the debugger, which we should take a peek at, in the debugger in the LC3, you can set it up yourself. Put the values in that you want to do. Like, let's say you have a program that pulls a value out of some location, pulls another value out of another location, adds them together, and stores that into another location. Well, you might not understand exactly how to get values out of that location. Maybe you're wrong about that. So one approach is you simply stuff values into those locations, and then you just step through just that lines of code to see that the values there show up in the registers. Yep, that works. Or you can skip that part and say, well, I'm not going to worry about where the numbers came from. I'm just going to put them in this register and add them together and put the result in a third register and see that it's correct. Like, manually inspect it and go like, okay, what's that number? Yes. What's that number? Yes, that is correct. Okay. Then I can worry about each of the different phases separately. Know that it works. Okay. Play computer on the paper. Get a piece of paper. Start writing the registers. Put it down. As you step through each one, change the values in the variable locations and in memory and in the registers. You have to know where the program has gotten to. You can step to that point. You can set breakpoints. In classic old languages, we used to do just print statements, which you can still do in things like Python, right? Like just put a print statement here whenever I get to right here. Even maybe a pause, so I have to press a key and then let it keep going. That's really it's kind of like rudimentary debugging, but also kind of high level, in the sense that I'm actually just writing my own little debugging code to stop or spit out what the value is. You know, the value is now, like, for example, let's just do like so Chris did the you know, for I in range eggs, right? Like Python-esque. And that range in Python is a little funky, right? Because sometimes you're like, wait, range 10 goes 0 to 9, and right, and that kind of stuff. Yeah, breakpoints save lives. That's right. Check your breaks. But you see what I mean? Like, that'll throw you off. So one approach is like start into your loop and spit out I. You know, like I, you know, colon, and you're like I 0, and you're like, oh my gosh, that's right. I starts at 0. Or maybe you're in a language where I starts at 1. You know, it's not consistent. So spitting out information as you go via just print statements is fine. Okay. Check values. Yeah, debugging tools. Now, what I think I'm going to do, here's the thing. This is an example, but I don't want to do it. I don't want to do this. And I need to, let me see. Yeah, yep, I'm not gonna, that's it. That's it for these slides. I mean, there's a couple things I want to do. But yeah. So that's actually the end of the lecture stuff for chapter 6, which is really just about the lectures are about design, stepwise refinement, and debugging. The homework is really more of the same. It's more programming, only they're bigger program segments. So you see what I mean? The lectures are more nudging you toward a little bit longer programming. The homework is about, you know, moving from 1-2 lines to 5 lines, 10 lines, and nurturing that, okay? Getting you to grow that a little bit more. What I want to do is just take a minute while we're in this mode of talking about debugging, and blow this bad boy up. This is your friend. How are we doing on, how's that visibility? Is that okay? The problem, I don't know, is that okay for you?
It's a little blurry, but somewhat readable.
Yeah. I mean, the thing is, okay, let me just draw you. I'll blow it up a little bit more. This stuff we don't care about yet. That's the console. This is like little scrolly up down stuff. Jump to the program counter. This is actually doing your code, assembling your code. Okay. And then these are the ones we really care about. So I'm going to make it a couple more big, okay? But just understand that these are down here. Okay, we've got to scroll down to it. And what I want to do is I want to just let you guys drive this a little bit, but just kind of walk through some of the, let's do some programming, shall we? Let's do some programming. The first thing I want to do is just remind you, if you program in machine language in this LC3 interpreter, the very first number that you put here And by the way, I'm going to try an experiment. I think this might actually work. It's way easier to read the binary, right? If you just separate it. I think this might work, and this is how we, like, I don't know. Let's try. This says 3000, right? That should start our program at location 3000. And all I want to do is a halt. And what was the trap instruction? Somebody's got their... I can pull that up real quick as well.
That should
instruction.
be 0. That should be 0000 for the first 4 bits.
You're right. Yeah, oh, yeah, absolutely. That's right, because it's 03. No. You're wrong.
All right. Yeah. Oh wait, that's a break, isn't it? BR.
Oh, so I was just doing this
Or
one
branch.
as the starting address. Then,
Oh, okay.
yeah, then the trap, it's the trap instruction. Let me pull up that instruction set and drag it over, kind of over the top for now, and we'll scoochie it back out of the way here in a sec. Yeah, so trap is 1111, and then we have 4 zeros, and then a trap vector 8. Okay, so now this is the halt instruction. Okay. And the halt instruction just stops the program. So we always have to have a halt instruction at the end. Now these 4 are going to be, so it's 2, 5. So that's 2 and that's 5, right? Boom, there's 2, that's 5. Now I'm going to try to see if it'll be okay with those spaces. Oh, yeah. Okay, good. I don't know that I've ever tried that, but that is, you see how much easier that is to read? You know, when you're trying to just separate it. You can also do this like the way the instructions are breaking it up. You could go, for example, like an add instruction and go 4 and then go 3 space, 3 space, 3 zeros, right, space. You can separate it to make it more readable. As long as it's all just bits on a line, the LC3 simulator is going to be okay with that. Okay? And then you hit process, and then you load it into the thing. So you can see it's right there. This whole program is one instruction, which is a halt. And if I say run, halting the processor. That's all it does. That's it. Now I've got to unhalt it to be ready to go again. I can clear the registers. I can reset all the registers. The program counters back to 3000. I can clear the output. Okay, so what I want to do is I want to go back to, let's do something before we get to the halt. Is there something nagging you? We can just do something straight up boring for now. Let's do, should we do an and? Because you can see an and, you can see the result of an and really quickly. You know what I mean? Add, you have to like look at it, maybe convert it to decimal. But and, you're like right there. You can kind of see it. All right? So and is 0101. And you tell me, I mean, I'm going to roll, but tell me if there's a certain way you'd like to do this. We can do it, so there's got to be 3, so there's a destination register, a source register. So destination register, let's just make that 1. Oops. And we'll make this first source register, register 2. I feel like I screwed the ever-loving heck. I messed the...
Yeah, there you go.
Yeah, I screwed that all the way up. Then here's the question: do you want to do the immediate, or do you want to do value? Let's do. I don't know. What do you think? I don't care.
Let's do immediate.
Okay, let's do immediate. So that means we go 1, right? And then we've got 5 bits for the immediate value. So let's do this. We'll just put that, that's just going to clear everything, right? That's going to blow everything up, right? And then let's just process this for now. So that's going to take R2 and it with Zilcho and put the results into R1, okay? Now, the thing is, of course, this is pretty boring because all these values are nothing. But what if I take R2, see what I can do? I can just click on that. And what if I go, I'll make it all F's, just F, 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 right? Now what I'm going to do is I'm going to go just step. Well, I'm going to go next, which will skip past. Okay. Now, do you see what it's done over here? That's the instruction we just built. That is the instruction when viewed in assembly language. So also, if you play with this simulator, it starts to teach you about assembly language and creating a mapping between the machine language and the assembly language. So there's an AND. Destination is R1, goes R2, goes into 0. Okay. So I can go, okay, let me do next. Yeah, nothing interesting happened, right? Nothing survived. Took R2, I cleared the whole thing out. So let's do something different. Let's make this like something that'll leave the last 3 bits and clear everything else. Remember that this guy, when you do the AND, it's going to sign extend it. Well, it's going to sign extend it whether you do an add or an AND. But what this effectively going to do as a positive number on the AND, it's going to still get extended with zeros when it goes to do the AND. Okay, so now do you see what we're ANDing with? 7. And I haven't done anything. I can also, I can reset the registers. Get me back, kind of start. Set this guy up again. So he's ready to go. R2's ready to go. We're going to AND it with 7, and we're going to put the results into R1. Ready? Go next. Boom. See the 7? That's just all zeros, 1, 1, 1. We didn't run the halt, but it's okay. You see all we're doing? We're just like, try a thing, do a thing, experiment with a thing. Know that that works exactly the way you wanted it to work. Let me try one other thing I'm just curious about. If I do that, it's an immediate 5. I believe that it is going to sign extend that, and it's going to turn it into FFFF. See it? Yep. See what it says it is? -1. Okay, let's reset the registers. Let's make this one FFFF again. Okay, ready? And we predict that R1 ought to be all Fs. Oh, yeah. Cool, right? And we're just messing with one instruction, but we can put values into the registers, or we could even write a little code that like puts a value in the registers for testing, Okay, let me do one more because we're getting close on time. And there's one that, here's the one. Let's go LEA, okay? That's load effective address. Let's just say that we have over here location 3, I'm a dork, 3002, and that's like a variable, okay? Let's just say that's our variable location. It's after the halt. You can't accidentally run into it. And we're just going to use it, okay? So we want 3001 to be this place where we're going to put stuff. So what we want to do is maybe we leave the whole setup the same way. But we want to maybe put the answer into this variable location, 3002. All right? So what we want to do for starters is we got to get that address somewhere, right? So we can do a store instruction. So we're going to do the LEA. So that's 1110, and we're going to do it here at the very beginning. We're setting it up. So that's LEA. The destination register doesn't matter. We already used 1, 2, and 3. Why don't we use 4? There's 4. And oh yeah, and the rest is PC offset 9. Okay. Well, when we are executing this instruction, the program counter is going to be 1 past it, right? So it's got to be 1. It's the program counter plus 1. Everybody buying? It's 9 bits. There it is. Now, okay, but you're like, okay, I don't know if I got it right. Dr. K, did I get it right? I don't know. Let's find out, okay? So here we go. We're going to do a LEA. Now, check it out. Check it out. This is what's so cool. First of all, I can tell you that we're wrong. I can tell you we're wrong because it already said that we're going to put this value. It's already calculating it for us, and we can look and see that it was not correct. Okay, what did we do? Well, one way to figure this out, let's reset all the registers. And let's make this go FFFF again. Okay. So the first thing we're going to do is when we run this thing, the program counter is going to be 3001, and we said +1, but we just dorked it because it's here. That's 1. It needs to be 2. Can you see it? And if we do it, in fact, let's do it. We go next. See that R4? We loaded the effective address into R4, and there it is right there, 3002, and it's not correct. And if we do the next stuff we're going to do, we will overwrite that instruction. So let's go back here and fix it. That's 2. Process, load it. Okay, now see what it's saying? 3003. Yep, that's correct. It's after the halt. That's the one we were going to use for our variable. Okay. What happens next? So we load the effective address of this instruction, which is 3003, into R4. And by the way, let's just do it. There we go. We're going to do the AND. So now R1 has that value. Now what we want to do is we want to put the results into memory right there. Is this kind of cool? Tell me this is cool. I think this is cool. I'll just say it. I think it's cool. Okay, then we're going to do a store.
It's cool until you forget which registers are holding what.
No, right. No, that's why you have this, okay? And comments. In assembly language, you have comments. Oh, you know what else, by the way, you can actually do? In this assembler, you can go like this. I'm not sure how to spell Flibberty Gibbet. It's okay. You can put comments in your machine code with just a semicolon. And whatever comes after that is just a comment. So you can remind yourself if you want to do it that way. And I want to apologize for misspelling Flibberty Gibbet. Okay. What am I doing? Oh, yeah. Store. We're going to use store R because we're going to take a source register and we're going to put the contents of our source register, which is R1, and we are going to put that wherever our base register is telling us to put it, plus an offset, which we don't have, we don't care about that. So STR is 0111. Okay, let's see. So we did the instruction, and we go 0, 1, 1, 1, right? That is the STR. We're putting it from register 1, and we're putting it where R4 is pointing, right? And offset 6, which we're just going to go just all zeros. Process. And by the way, if you screwed something up on the syntax, it'll puke right there on you. Okay, now, anybody see a problem? Well, we just created a problem. So we're going to load effective address into R4. We're going to AND R2 with -1, put the results in R1. Then we're going to take the results that are in R1 and we're going to shove them into R4, wherever R4 points. What did we screw up? Bueller's. Who can see it?
Oh, since we added a new instruction, didn't it get bumped down one?
Exactly, right? And this, by the way, is meant to illustrate for you why machine language is such a royal pain in the backside, because we hard-coded a value. We said two past the program counter. Then we added an instruction. It's not 2 anymore, it's 3. With assembly language, you can use labels, and then the assembler automatically adjusts that offset for you. But when you're doing machine language, you don't have that. So we got to go back, and at this point, the program counter will be here. 1, 2, 3. So right there, that's 3. That's looking better, right? Okay, so let's do this thing. We're going to reset all the registers. This one we're going to set to be all Fs. Okay, are we ready? First of all, let's just do it this way. Run. Nah, I don't want to run. It makes me too scared. Let's do next. R4 should acquire the value 3004. Boom, there it is. See it? Program counter's been incremented. We're going to now AND R2 with -1. Should survive. But it's going to show up in R1 as FFFF. Now we're going to store. Now what you want to be looking at is this value right here. Okay, that value, which is currently zeros, but that's location 3004. This is now going to be a memory location. It is a memory location. It's now going to be a variable in memory. Okay, ready for next? It should take the contents in R1, put it into wherever R4 is pointing, which is 3004. Boom, do you see it? Do you see it? Now, I don't know what we did and why we did it. You know what I mean? And in fact, this actually put in the dot fill and said it's like data now. It just looks like, it looks to this like data, even though, you know, don't worry too much about that yet. But do you see what I mean? We wrote a little program that was 1, 2, 3, 4, 5 lines of assembly code, 4 lines of real instructions, 3 really, and a halt instruction, and a single word of data, 2 bytes of data. And, you know, it didn't do anything fancy, but it's a piece of something, you know, that could be doing something else, right? Also notice, we didn't really track it, but notice that the instruction register is pulling the value that we just did. And then if I just let it go and run, it'll go and, you know, run to the end and run the wrap-up code. Anyway, kind of cool, right? But you see how even with that little bit of coding, there's a little debugging to go on. You know, like, okay, that doesn't seem quite right. Now check this out. I want to just do one other thing. Let's do it again. Only the one thing I want to do is we don't fix our bug. We don't fix that bug. It's still 1 off. Notice that the assembler's like, oh, really? You want to overwrite the halt instruction? Great. Great. So here's what happens. Check it out. So we're all ready to go. We go next, right? That loads 3003. And then we do the little math thing that puts -1 into R1. Now we're gonna store our value into 3003. See what we just did? We just overwrote the halt instruction. And now, where's the program counter? 3003. The program counter is now going to run all ones. What is it? It turns out that there's a fail-safe for certain kinds of instructions. This is not actually, it'll get to the halt instruction, but it's more complex than, it just so happened to be that the value we wrote there was all ones. But if it had been all zeros, it would have looked just like a no-op, no branch. But that's the problem. You start overwriting data, you start overwriting instructions, and then jumping to those, and you get random. You get random crap. Okay. Is that cool? Hopefully, at least demystifying a little bit. This simulator has got to be your friend. It has got to be your friend. It works just fine running from the web. You can also grab a command line version if you prefer to run that way. Okay. But it's easiest to run it from the console. All right, so that's what I got. We are finito with number 6, which means we will set up a deadline for module 7. 7. I've said this before. The modules will speed up, but they're not as big conceptually. They are smaller chunks, and they'll speed up. But you'll be acquiring, points down the stretch, at a disproportionately high rate for the concepts. You know what I mean? You'll be getting module points, and it'll be fewer concepts than you would have had in modules, 2, 3, 4, especially, which are kind of the heaviest modules. Okay, friends, that's it. That's what I got. So, wish me luck freezing my ever-loving tush tomorrow morning on set. And I will be back on Thursday to jump into Chapter 7. Whatever that is. I'm sure it's something cool, but we'll figure that out.
Thanks,
Okay.
Dr. K.
You bet. And Mike, yeah, if you Google the LC3 simulator is the first result. And I have a link in the syllabus as well to help you. So, and yes, Mike says, well, assembly makes it a lot easier. Yes. We start
Oh
here.
yeah, once you get going with assembly, it just gets a lot smoother, because the thing is, like, machine code is just like super tedious, but assembly, you have like shortcuts that you can do. So
That's
it's
right.
just
That's exactly right.
a lot better.
Yep. Right on, man. Okay. All right. See you, everybody.